Okay, so what actually is ControlNet? You've got like these 8 models, and you've got this, and you've got that, and you've got the other. But what's actually going on here? There are a lot of videos out there explaining how to use ControlNet, but that's not what we're doing today. This video is about the underlying mechanism. So we're going to answer 3 questions. Firstly, what is ControlNet? Secondly, how does ControlNet work under the hood? I love saying under the hood. And thirdly, why should we care? Why does it matter? Is ControlNet actually important from like an AI research standpoint? So if we answer all these 3 questions, then we've done a good job. So what is ControlNet? It is a research paper, very good research paper, I might add, and an associated GitHub repository. The paper is actually very readable, so if you're a paper person, you're actually going to have a lot of fun reading this paper. And in this research paper, these 2 excellent researchers present a new means of fine-tuning a stable diffusion model. In fact, this method could be applied to like any number of models, but they apply it to stable diffusion in the paper. The researchers claim that this method is super effective, and to prove their point, they trained 8 different models to perform like specific subtasks related to stable diffusion, and then they spent ages giving us all these nice image comparisons of all the different models and proving that the models were like really good. So that's the view from 1,000 feet. ControlNet is a method for training stable diffusion to complete specialized subtasks. ControlNet isn't like a single model, it's a model training mechanism. But how does this training technique work exactly? Well, the best way to explain it is to start with the motivation. So at the moment, stable diffusion is like a really good, really powerful model, but there are some things that it simply can't do that maybe would like it to do. So imagine that you wanted to get stable diffusion to give you an image of Jesus dabbing. And you open up whatever program you use for stable diffusion, and you're like, okay, I want an image of Jesus dabbing. You put in the text, and out comes an image like this, which is pretty close. You can definitely see that stable diffusion is a very clever program. You know, it knows all these things about compositional elements, it knows what a human looks like, it knows about lighting. The image looks pretty realistic and good, but the thing we're missing is the actual dabbing here. We're not able to be as specific as we would like. So ideally what we'd want is to be able to feed more inputs into stable diffusion. We'd want some other model, that's not stable diffusion. Stable diffusion can't do this. We want a model where we can give it a text, and we can also give it some other kind of input. In this case, like a depth map would be a really good example of something we could give it. We could take a depth map from this image. It turns out that it's quite easy to extract depth maps at this point. There's very good models to do that. So we could extract the depth map from this image and pass it in. And then along with the text, this hypothetical model should be able to do better than stable diffusion has done in generating an image like this. Just by the way, it's conventional to refer to extra information you provide to a latent diffusion model as conditioning. This is something that comes from probability. The idea is that the model is spitting out some kind of image, and if you pass in the text, you're sort of conditioning the output on that image. Or you can say that the output is conditional on the text you give it. So ideally what we want is a model that can take other forms of conditioning, like say a depth map. That's what we'd like, that's what we're looking for. And again, stable diffusion can't do that. Its architecture is only built to take in text. Or of course you can do image to image. You can take this white noise and you can replace it with an actual image, which will help the process get closer to what you want. But nevertheless, there's only one source of external conditioning, which is the prompt. But we don't want to have to train this model from scratch, because we already know that stable diffusion is like really close to what we want. It's got so close. Considering the huge, immense space of possible images, this image is so close to what we want that, it's tantalizing us at this stage. So starting and trying to train a model from scratch, that seems silly. We want to somehow be able to leverage all the knowledge and the wealth of weights and training that's been done to this model, and then put it into a new model that can also take this additional conditioning input. That's what we'd like. And so that's sort of the question that the authors were trying to raise. They were like, hey guys, what is the most efficient way to do that? What is the most efficient way to train a model to take in additional conditioning inputs? And this is exactly what they say in the first sentence of the paper. We present a neural network structure, ControlNet, to control pre-trained large diffusion models to support additional input conditions. So that's what this whole paper is about. Okay, so these guys have to create a new architecture that leverages the stable diffusion weights that already exist to quickly build a model that can take an additional input. And how do they do this? Well, kind of in a pretty straightforward way, actually. Now, if you read the paper, there's actually a lot to it. They have this complex architecture where they make a bunch of like very opinionated design choices. They invent something called the zero convolution. They have a bunch of math to back it up. But I'm just trying to boil this down to the biggest thing they do. So in the highest, broadest possible sense, this is how ControlNet works. You take your stable diffusion model and you freeze it. So you prevent any gradient updates to it. You make sure that it doesn't change at all. You just have this locked, frozen stable diffusion model that doesn't change. In addition to that, you create an external network. In the paper, they refer to this as the trainable copy. And you give the external network the responsibility for handling whatever new conditioning input you're giving it. In this case, a depth map. So you allow this external model to take in a depth map. And then you also create a mechanism for allowing the external network to flow information into the main model. So the idea is the external network learns what the depth map is and how to understand depth maps and how to use them properly. And the external network pushes that information into the main model, the initial model, sort of injects that information in there, and we'll get to exactly how that works in a second. And in this way, the main stable diffusion model is able to take the new information into account without actually updating its weights at all or changing in any way. This idea is very closely linked to something called a hypernetwork, which is a term you may have heard floating around a few times. It seems to be a pretty broad term. People use it to refer to things that are a bit different. But basically the idea of the hypernetwork is you have a very powerful, big, strong model that is really, really clever. And to make it perform on a subtask or a new task, you create an external network like this one to sort of assist that model rather than training the model itself. That seems to be sort of the hypernetwork strategy. To do sort of like a bad analogy, it's like you have a law firm that specializes in tax law, and one of your lawyers is really excellent. She's like the best tax law lawyer in the country. And then suddenly the market changes and a bunch of contract law cases come up and you need to do a bunch of contract law now. And the taxation lawyer, she doesn't know anything about contract law. So rather than getting the taxation lawyer who's like the best to go back to uni and learn about contract law, you hire a contract lawyer who's like maybe a bit junior, and the contract lawyer sort of handles all the contract law stuff and then passes the information in a really palatable way onto the tax lawyer, and then she's able to understand what's going on and make the right decisions and make the right calls. I don't know what lawyers do, but she can write the contracts without actually having to know anything about business law herself. So that's kind of the idea behind control nets. The actual control net itself is this whole thing. So the whole thing can be thought of as one model, the external model plus the SD model. So for instance, if you go to the Hugging Face page the authors set up, you'll see there are all these like big 5 gig models. These are all the full control net, right? So it's a Stable Diffusion 1.5 model plus tacked onto it also this external model. So this is why it's a bit larger than just a normal Stable Diffusion model. Whereas if you go to, say, this WebUI repo, there are a whole bunch of smaller control nets. It turns out these are only the external network. That's all they are. And the expectation is you'll download the external network, plug it into, say, your automatic 11111 WebUI, and the WebUI will pair that external network with whatever Stable Diffusion network that you're already using locally. So the control net is like both of them together, but you can also just download these external networks and throw them around. Obviously, if you train the external network with a particular Stable Diffusion model, it might work really badly with a different model that it hasn't been trained on, because there's probably quite a tight bond between the external network and the model it was trained with. And obviously, if you try to use a different version of Stable Diffusion, it's not going to work at all because the compatibility is set to like 1.5 because that's what the author's trained on. So hopefully now, all of us, everyone has a pretty good conceptual understanding of what ControlNet is and how it works, but I want to get a little bit more technical because I find that really helps my personal understanding. So buckle the heck up, okay? A single forward pass of a ControlNet model consists of you taking the input image, which is usually noise, but it could be maybe you're doing image to image instead, so it could be a particular image, and you pass that image both to the external and to the frozen model. You also pass the prompt to both models as well, and then finally you pass the conditioning, the extra conditioning information, only to the external network. The information flows through both models at the same time, and then about halfway through, the external network starts shoving information into the main model. If we want to zoom in a little bit more, it'll end up looking a little bit like this. So the external network has a bunch of encoder layers, which are very similar to the encoder layers of the frozen network. And you pass the conditioning information in, and then each layer is linked to a particular layer in the internal network. The layer in the external network will pass the knowledge it's gained, the information it's extracted from this conditioning information, into one of the internal layers. So let's zoom in a little bit more. If you look at the internal workings of a stable diffusion model, which, by the way, this is a pretty reasonable representation of how a stable diffusion model looks like inside. It's got these 4 encoder layers, got a middle layer, and then decoder layers. And, you start off with a big image, and then the image gets smaller and smaller and smaller, and then it gets bigger and bigger and bigger when you output it. There's a whole bunch of other connections and stuff in between these layers, but this is pretty reasonable. Okay, so if you just look at these 3 layers, what'll happen is that the 4th encoder layer, it'll pass out a bit of data. To be more specific, we'd call this a tensor, and it's just like a big blob of data, basically. And that tensor gets passed into the middle layer, which passes out a new tensor, which goes into the first decoder layer, and so on and so forth. The way that researchers refer to these blobs is as activations. Activations are the thing what gets output from a layer once you put an input into that layer. So they're just like outputs. Activations are just intermediate outputs. So when we add the external network, what we end up doing is rather than passing the activations from the 4th encoder directly into the middle layer, instead we add those activations together with the activations that come out of the middle layer in the external network. So we have this tensor, which comes out of the external network, this tensor, which is just flowing through the locked network as usual. We add them together, just a plus, just a normal like mathematical plus operation, and we end up with a new tensor, which is sort of a mix or like a blend between these 2 pieces of information. And the idea is that since the external network has taken this new conditioning information into account, now this new conditioning information is sitting inside the main model, and the main model can use it to its advantage. Okay, so then we pass this blended tensor into the middle layer. The middle layer produces activations, and then we mix those activations with the outputs from the last encoder layer in the external network. And then we produce another blend, which goes into the next layer, and so on and so forth. So if you zoom out, that's kind of what this looks like. You've got these arrows of the information going from the layers in the external network into the layers of the stable diffusion network. And the idea is that with that additional information, the locked network will be able to produce an output that takes this conditioning information into account. Okay, so now hopefully this really abstract picture and this arrow that's just pointing here makes a bit more sense, and it's easier to understand exactly what's going on there. And one more thing I really just have to mention about ControlNet. You'll notice that the external network, as depicted here, looks a lot like the first 5 layers of the regular stable diffusion model. And the reason that is because the paper authors were really keen on leveraging the knowledge and the information that was already in stable diffusion as much as possible. They were very much against training things from scratch. So you could make any kind of external network. You could train it from scratch, you could do whatever you wanted, you could make this any kind of structure you liked. But the paper authors were like, well, since we already have all this information in stable diffusion, what we'll do is we'll just copy out the first 4 layers of stable diffusion, unfreeze them, and allow them to be trained. And that will be our external network. So that's what the paper authors did, and that's probably, that decision probably had a big impact on their results. But in theory, you could have any kind of external network you liked. Okay, and one last thing to make just completely clear here is that you actually end up training this external network. So you get your huge data set of image caption pairs and you pass them into the model. And each time you do that, you also generate a depth map for the image. And you just do the normal stable diffusion training routine where you get it to create an output and then penalize it for producing outputs that are wrong. And you just do that for as many iterations as you need to, but you never update any weights inside the main model. You just update weights inside the external model. So again, I want to emphasize that ControlNet is a training strategy where you do usual, regular stable diffusion training stuff to train this external network instead of the main network. Okay, so now we can go ahead and do the really fun thing where we draw a tick in this box and say, we now understand how ControlNet works. Again, the authors made a whole bunch of really interesting decisions that a lot of them seem really cool. And to really understand it, you'll probably have to read the paper. But this is sort of the very high level. Okay, last one. I have actually tried to make this video like 5 times, and I think I'm just going insane. I'm just finding it really hard to condense my thoughts properly. But we're almost at the end. Why should we care about ControlNet? Is ControlNet actually important? So obviously ControlNet is seeing a lot of uptake. If you go to the GitHub repo, it's on like 12,000 stars. The reason that I think ControlNet is interesting though, is that they kind of made a bit of a weird decision. Normally, when you're training a big model to perform a subtask or like a task very similar to the one that it already does, you actually just go ahead and train the model, right? Like ControlNet does this weird thing where it locks the model and then creates an external model and like hires a contract lawyer or whatever. Usually what you do is you just take the really knowledgeable, powerful model, you add some new inputs to it, and maybe like a few weights so that it can handle those inputs a little bit better. And then you just proceed with normal training with the new inputs and the new expected outputs. And then after a while, what you'll get is the model that now performs your new task. That's like the standard paradigm for fine-tuning, right? Just take the existing weights and then train them a bit until they're new weights. For instance, that's exactly how Dreambooth and LoRa work. I've done a video on those if you want to know what they are. But anyway, that's how they work. You have your normal stable diffusion model and then you give it a few images of your face and then you just keep training it like usual and update the weights inside the model until it understands your face. And that's like the normal thing to do. But the ControlNet guys were like, no. We're going to freeze it and do an external network. And for some reason, we think that's going to work better. And like it kind of does actually work better. And I say that because there's actually this really nice comparison out there. A few months ago, Stability AI, along with their Stable Diffusion 2.1 release, released this model called Stable Diffusion to Depth, which is more colloquially referred to as depth to image. This model is highly cool. It was trained by the same researchers who did the original latent diffusion models paper. It takes an image and a depth map and then a prompt, and then it allows Stable Diffusion to create images that match that depth map, which obviously that's really cool. And the method that the researchers used when training Stable Diffusion to Depth or depth to image was exactly the one I described before. So all they did is they unfroze the model, added like a tiny extra sliver of weights onto it so that it could take this new image into account. In fact, the way they passed this new information in was just like as an extra channel. You know how images have like 3 channels, like red, green, blue? Well, they just added like an extra one, which was like the depth map layer. They added a few more weights to allow Stable Diffusion to process that new layer, and then they just kept training, just like normal. And they ended up creating this depth to image model, which works like actually fairly well. And so the ControlNet guys, to give themselves a nice point of comparison, went ahead and trained exactly the same kind of model, but using the ControlNet strategy. Here are the results they got, and this is kind of a little comparison the authors did. These are the images that come out when you use depth to image. These are the images that are coming out when you use ControlNet. The authors claim that their results are like a bit better. I'm always really skeptical when authors do that, so I decided to do my own little study. So I just downloaded this image of this gentleman dabbing from the internet. I created a prompt that described what I wanted, and then I passed that into just regular image-to-image Stable Diffusion. And then I also tried the same thing with depth to image, and then I tried exactly the same thing with ControlNet. And then here are the results. Like, judge for yourself which ones of these are better. But from what I can see, the image-to-image results are like pretty bad because none of them are actually dabbing. The depth-to-image results are a lot better. They're way closer because the sort of arms seem like they're in the right position. But none of them actually look like they're dabbing, really. Whereas the ControlNet images, every single one actually looks like they're dabbing. And some of them give like a really sharp, like, that's like a good dab. Like, that's a dab, you know what I mean? Oh, that's a good, ControlNet seems to have significantly better fine-grained control. So if you look at these images, you'll see that they all seem to have these sort of perpendicular lines, like a little sleeve here. And the shadows on their garment, the shading of the garment, and like the fabric seems to lie in this pattern, which is very similar to the pattern on the original image. You can also see these sort of perpendicular lines on his shirt. Whereas all of the depth-to-image models, they don't have that, or like most of them don't. So I thought that was very impressive that it's able to capture these sort of fabric details just from a depth map. So I don't know. This is by no means a conclusive study, but as far as I'm concerned, ControlNet seems to be a bit better. That's not the important bit though. The important bit is that depth-to-image was trained for more than 2,000 GPU hours, or at least the authors estimate that's how long it took, and that seems to be about right, on A100 GPUs, which are like really chunky, like industrial grade GPUs. In 2,000 hours, that's like 3 months. Whereas ControlNet was trained for less than 1 week, right? That's like 168 hours on a consumer grade GPU. So that's kind of, that's big. That's like an order of magnitude improvement in terms of training efficiency. And it's kind of a little bit rare in research that you see things that are orders of magnitude better. So that's actually kind of exciting. And if we're really lucky, it means that this method here, this sort of external like hyper-network approach to fine-tuning, is actually a lot more efficient. And little guys like you and me who don't have a house that's built out of A100s will actually be able to do really cool stuff. And of course, now there's this obvious question, which is, why is it better? Why is it so much faster? We can kind of answer the faster question, and that's because when you're training a ControlNet, you're only training the external network, which is like smaller. In this case, it's about half the size. And because it's smaller, it's faster to train. You're only updating like n weights as opposed to 2n weights. So that's probably why it's faster. Why is it better though? That's kind of hard to answer. The authors claim that the reason they decided to go with this ControlNet strategy in the first place is to avoid overfitting when the dataset is small and to preserve the production-ready quality of the large models. Which basically means that they're worried that if you fine-tune the big model on a small dataset, or I suppose a dataset that's like kind of complex, you risk ruining the weights in the model to begin with. So I guess the theory is that if you give like a completely new input to this very specialized model, it's gonna kind of wreak a bit of havoc for a while. If you expect that really good model to score really well on this new input immediately, you start punishing it for not performing well immediately, that might cause some issues. And that might mean you'll have to train for a long time before you end up getting good results. Whereas if you lock the model and say, no, the weights in this model are good, don't touch them, do all the training in a different network, then the training process will go faster. In this case, we have an external network. You're sort of locked into this very good baseline. You can't stray too far from this very good, effective regime, which you're locked into. Something along those lines. And then the nice thing with ControlNet, which is something the authors point out, is that once you've finished training and once you're getting these good outputs using the external network, then you can go ahead and unlock the main network and then do a bit more training and allow this main network to take some of this information into account as well. And in that case, you sort of don't really risk doing damage to this model because it's already so close to good outputs anyway. But that's like pure conjecture, okay? So forget I said any of that. We don't actually know why it's faster or why the images seem to be better. Those things we have yet to determine. Okay, looks like we're done. Happy times. Let us summarize. So what is ControlNet? It's a new way of doing fine-tuning, teaching powerful models to perform subtasks. How does it work? Well, you lock the original model and then create an external model, which you then train to understand the new inputs, and then flow that data from the external model into the main model. And why should we care? Because it seems to give better results and take an order of magnitude less time to train than the orthodox approach.